So for our honors fluids project, we presented on Schlieren imaging, building up the setup, and then running certain things through it and visualizing the different flows over it. So this is from Lars, Jonathan, Ben, and Weston. First picture here is a picture of our setup, how we went about actually achieving the imaging. Most of this was all just based off of different experience that people have done before. The top picture on the right is the theoretical image of what's supposed to happen. We have that light source, which is just a point source of light bouncing off of a concave mirror, coming back onto a knife edge, and then a camera placed right behind that. The whole reason this works is because light is going to refract differently through different densities of fluid, so that allows us to see when fluid changes different temperatures or different speeds. We can visualize that and then run certain objects in there and see how it flows over things. So the bottom right here is our actual setup. On the very right, you can see we have our concave mirror set up. It was on kind of a sliding system, so we were able to make fine adjustments to that. This depended very much on everything being stable and in the right position. Our point source of light was just a LED source with some tinfoil on the front with a hole poked through, so we were able to get a fairly bright light that was just coming off of one point. And then the camera right here was, we were able to move around in order to really get that image that we need. So we kind of set this up basically according to this figure here, and then iterated over until we finally focused the light through the camera. So the hard part was finding that focus. We weren't able to just focus on the mirror. We were instead focusing on this focal point at that knife edge there, until the light basically refracted off the top and bottom of the camera and filled the entire image of the camera. And then we used different things like heat guns and candles, and we're able to visualize the hot and cold air and the movement of air across the mirror, which is pretty cool.
All right, so to start, one of the first things we decided to test were streamlined bodies. And we just wanted to see, when we put that in front of the flow, if the flow would stay attached as it went across our objects. And so you can see in this first video, this is an airfoil we'd made just out of like cardboard. But you can see the flow is pretty laminar, and so in this case it would be experiencing a lot of friction drag, but there shouldn't be any pressure drag. And you can see we also were changing the angle of attack, and so when we tilted it up, it started to stall. And so I'll play this again, and you can watch when the pressure drop becomes like too big for it to stay attached. That's when the flow separates, and you can see a lot of vortices happening on the top. And so on the second video, this was a model of an airplane that we had, like a Blackbird. And so we also saw the flow staying attached on this object. You can see the flow is very streamlined over it. And so this is what we'd expect to see. That it's, again, experiencing a lot of friction drag, but not really any pressure drag, because the flow is staying together. And so for the next thing we did, we had blunt bodies. And so the way that we tested this, we had a cylinder. And so we held the cylinder in two different orientations. The first one would be horizontal. So this would be kind of like the wire on the antenna of your car. And so we didn't have equipment to measure the Reynolds numbers, but this would be probably above Stokes flow, because as you can see, there's a lot of flow separation that's occurring on the backs. It starts to shed vortices. But then the second orientation, we held the cylinder, was just straight onto the flow. And so that would be very indicative of like a blunt body. And so it experiences a lot of stagnation pressure on the front, and you can see that as well, where the flow separates but especially on the front, that causes a lot of stagnation pressure. All right.
All right, so the next set of experiments that we did was frisbee golf discs. So in these, I started playing. We tested basically they're just things that flew that we thought were interesting. Some of us play frisbee golf, so we thought we'd look at kind of the different flows over them. So this first one is like a slower speed disc, or meant for slower speeds. So it's a putter. You can see a little bit of the boundary layer up here. There's not much flow separation just because it's just a rounded edge. One thing there's kind of a constraint of the experimental setup was that we were using a heat gun to cause the flow. So we were kind of constantly spinning the discs in the hope that they wouldn't like burn or light on fire. So we had it was a little wobbly on some of these images, but you can still see like most of the characteristics of the flow. And kind of for both of these, this was a mini frisbee golf disc that we kind of found around the house, just on a wire, and you can see it's got fairly laminar flow. There's a little bit of separation off the back as well. You can like just barely see the boundary layer, maybe not much, but there's a little bit of a wider area, and you can see a little bit when we change the angle. There's a little bit of drag coming off the bottom there as well, or not drag, but like turbulent flow. And then the next, let's see if I can get disc up here. So the next set of discs we did, or not set, we looked more at the back of them. So this first one, I believe, is a driver. So you can see kind of the flow coming over the top, the boundary layers, that kind of clear part. There's some little like turbulent flow sections coming off the bottom here, and then we kind of changed the attack angle a little bit. I didn't change much there, but when we like turned it up, it put off a lot on the bottom, and that's just because the disc had like a flat edge, or like an edge perpendicular to the flow at that point that was catching a lot of air. That kind of kicked it down. So and you can see, kind of, especially when it's just in flat flight, the driver doesn't have a lot of separation. It kind of is a fairly streamlined object off the back. So then this bottom one is the putter. So you can see here there's quite a bit of like flow separation, like you might see with a like blunt body. And that's, yeah, like Ben was saying, we don't have Reynolds number, but I would assume it's not Stokes flow because you're seeing that separation. So, and you see a little bit of the boundary layer there, but that was what we had for the frisbee golf discs. I get to skip again. Oh dear.
Okay, and then for the results, we yielded some interesting things. I think the main thing to take away was that the flow over the front of both those putter/driver was pretty laminar. You didn't see very much flow separation, but the big difference was in the wake off the back of each of these discs. So you could see kind of just very faintly this flow comes back together off the back of this driver when it's held flat, and it stays pretty smooth and laminar, versus on this putter there's just this kind of chaotic turbulent wake coming off the back. And the other interesting thing was when we changed the angle of attack. When we changed the angle of attack on that putter, that wake off the back stayed pretty much the same, just at a different angle, versus the driver just had this huge flow separation off the bottom. I mean, you could just see it looks like a rocket taking off, and it's caused by that lip that's underneath. And it was just interesting to see, because when we get into the conclusion of this, I think the main thing to take away was the putter was acting a little bit more like a blunt body, especially towards the back of it, while the driver is much more like a streamlined body. And this putter has a fairly, you can't call it flat because it's rounded, but a lot more of a even edge to it, not as sharp, a lot more blunt. So you get that flow separating at fairly the same spot, so it stays a little bit more stable, and kind of helps control it in the air, versus the driver has a super, pinched edge to it. And so if you throw it at a little bit too sharp of an angle, that's when you get that big, just, flow separation off the bottom. And so the other thing we wanted to recognize too is these discs are normally thrown with a good amount of spin, especially these drivers, which unfortunately we weren't able to test. But we still got some pretty good conclusions. I mean, if you kind of compare what the flow would look like over these blunt bodies, especially towards the back, I think you see a little bit more characteristics with the putter versus the streamlined bodies seem to look a lot more like this driver when it's thrown flat. The other thing I wanted to recognize is there's definitely places of error. Like mentioned earlier in this project, we had pretty much no idea what the Reynolds numbers were. Airspeed, light source could be shifting around, camera angle. It's a pretty fine setup, but we did get some pretty cool images. So we think that the results we did get are pretty reliable as far as seeing the airflow over these discs. And that's our presentation. Thank you.